This next graphic is illustrating how lime, the most common soil amendment to adjust pHs, is utilized. Lime is applied to acidic soils, meaning those that have pHs of 6 or below. If we have a soil with a pH of close to neutral but only slightly acidic, such as 6.2 or 6.5, it would generally not be feasible, or at least economically feasible, to lime this particular soil since it's still in a very desirable pH range. Generally, we don't start applying lime to a soil to adjust or increase the soil pH until pHs fall below 6. And in most cases, they're down in the low 5s prior to the time we lime that particular soil. So if we start out at the top of this diagram with a soil particle showing some exchange sites and cations that are being held on it in an acidic soil, you'll remember the earlier graphic we used that showed a high proportion of these exchange sites on the soil colloids being occupied by the hydrogen cation. Now obviously, if there are hydrogen cations on the exchange sites in high quantity, there must also be hydrogen cations in the soil solution around these soil particles in a soluble form as well. We would still have, of course, though, some basic cations such as calcium and or magnesium occurring on the exchange sites of those colloids in an acidic soil. So we come in and we apply lime as a soil amendment to raise the pH. Lime is calcium carbonate. If it's dolomitic lime, it would be calcium magnesium carbonate, but the chemistry of the reaction would be very much the same. Lime is going to dissociate, go into solution in the soil, and form calcium cations and carbonate anions. Because we greatly increase the concentration of calcium in the soil solution, calcium will now go on to the exchange sites on these soil colloids, and many of the hydrogens that are being held there will be displaced by the calcium. So we increase the calcium concentration in solution, causes it to go on to the exchange sites. It also causes the increase in calcium out here in soil solution, which actually causes a increase in the soil pH more into the neutral range. Now, it would appear, since we're kicking hydrogen ions off of these exchange sites, that would cause the pH to actually go down, since the amount of hydrogen in soil solution, or the active acidity, is really what we're measuring with that pH meter. However, many of these hydrogens that are displaced will then combine with the carbonate to form a bicarbonate ion. Therefore, if we're taking the hydrogen as a free ion out of solution, it's no longer there to be have this direct influence on the active acidity of the soil. Of course, we're going to also increase the concentration of calcium cations in the soil solution, which will also have an effect on soil pH.